Hello, my name is Constantine from Murenin. I'm currently a graduate student at the University of Waterloo, and I'm also the author of the latest revision of OpenBSD hardware sensors framework. I also previously worked as a summer code student in FreeBSD, and in addition, I'm a NetBSD and Dragonfly BSD commuter. And today I'm going to talk about quiet computing with BSD. I'm going to talk about my patch with fan control with CCTL AsiaBSDCon framework on OpenBSD and Dragonfly BSD. So the agenda of this talk is to slow fans down, not speed them up. And slower fans will result in less noise produced from the system. And less noise means that there's going to be less stress for the user. There's been some studies done that the environmental noise in the office, it generally causes additional stress for the workers. And if we reduce the noise, then we reduce the stress. And less stress means that workers will have more motivation. So in my work, I concentrated on commonplace desktop hardware because, in my opinion, that was the most important thing for me to run OpenBSD on and BSD systems on, for my personal use. And wing-borne superior chips, they are ubiquitous. Most of the computers, if you buy a motherboard from AsiaBSD or from MSI, it is very likely to have a wing-borne superior chip. So by supporting wing-borne superior chip, I support most of the desktop hardware out there. A lot of the desktop hardware out there. And also one of the main points about my work is that I didn't try to reinvent the wheel. A lot of the chips, they allow you to do in-fan thermal control. So you can specify that you want a specific temperature to be maintained in your system. So for example, you want the system to run at around 60 degrees centigrade. And then if the temperature sensor indicates that the temperature of the system is less than 60 degrees centigrade, then the chip will automatically engage the fan, so you won't have, operating system will not have to do anything. And if the temperature goes above 60, then it will be engaged, and if it goes below 60, then it will disengage. So I'm going to give a brief introduction about the alternative options that are available for fan control. And as you can see in this picture, this is a screenshot of the BIOS of the Intel D201 GLY2 board. And you can see that if you go into the BIOS, into the advanced section, into the fan control configuration section, there is an option for system fan control. And the only options that are available in this BIOS is disable and enable. Now some BIOSes, they offer more options, but a lot of the BIOSes, they don't offer any options at all, whereas the chips that is included in the motherboard, it actually does support fan control. So that's the reason why I wanted to work on this patch, because the systems that I had, I knew that they could potentially do the fan controlling, but there was no options in the BIOS to do fan controlling. So I wanted to come up with my solution for BSD that would allow me to do fan control. So another alternative for fan control that is often cited is fan control through ACPI. And ACPI has a notion of thermal zones with active cooling objects. And it also has a concept of fan device with a binary state. So a fan device can be on or off. And fan device doesn't have to be an actual fan. It can be a setting on a certain fan. So for example, a fan device, one of the fan devices can be a setting of 50% on the fan. So if it's on, then it's running on 50%, and if it's off, it's running on a different state. And there are temperature thresholds. ACPI defines temperature thresholds for fan device engagement. So for example, if we reach a temperature of 60 degrees, then a certain fan device may be engaged. If we reach a temperature of 65 degrees, then a different fan device may be engaged in addition to the previous one. And the fan control for ACPI is still rarely available on commonplace desktop hardware. So most of the Taiwanese desktop boards from AsiaBSD or from MSI and from Gigabyte, from these manufacturers, they still don't have control for thermal zones in ACPI. So fan control for ACPI is not very useful for custom assembled boxes anyway. And the reason is that it's not very useful because when you buy a motherboard and you put it in a custom case, then the motherboard manufacturer, they have no idea which case you're going to select and how many fans you're going to connect to the motherboard. So it doesn't make much sense for the motherboard manufacturer to define the fan control, the fan devices in AsiaBSD, because it doesn't actually know what fan devices you're going to use, what you're going to connect the motherboard to. So fan control for AsiaBSD doesn't make much sense for custom assembled boxes. So if you buy an assembled system like from Dell, then it makes sense because Dell knows what fans it puts into the system, and AsiaBSD can function nicely with branded boxes. But with custom assembled boxes, it doesn't make much sense because of these reasons, because you don't know what fans you're going to have. So fan control in Windows. In Windows, there is a popular program called SpeedFan for Windows. And it is closed source, so it's not possible to see what code they have. And it can control the duty cycle of the fan. So you can set the fan cycle to 50% so that the fan doesn't run as fast as it would have otherwise. But this program, it lacks interfacing for in-chip thermal-based control. So with this program, you cannot just say that you want the chip to automatically try to have the system temperature at 60 degrees centigrade. And if your temperature goes below 60 degrees centigrade, to turn the fans off or to cool them down, to turn them at lower speed. And if it goes above 60 degrees centigrade, for example, to make them run at higher speed. So SpeedFan, it only allows you to set the duty cycle of the fan in the chip. You cannot select the temperature cruise control settings of the chip. And most chips, they do control temperature cruise control. So the software, I don't find it very useful because, for example, if your system freezes and you set temperature to the speed of the fan to 40% duty cycle, then it means that if your system freezes, it likely goes into the idle loop all the time. It goes into the loop all the time. And it's likely going to consume more power resources than if it didn't freeze. And it is likely overheat, and it will likely shut down. And there may be, under some rare circumstances, there may be some damage to the system. So I don't like this software because it doesn't support those things. And it's obviously not available for BSD. So fan control in Linux. In Linux, there is a package called LM sensors. And in general, it is thought to be too difficult to configure. And of course, it's not available on any BSD systems. So we're not going to go further into that because it's not available in BSD. So next, let's try to see what kind of fan control options are available in Winbone Super hardware monitors. So they offer several fan controlling options. One of them is a manual pulse width modulation, or DC fan control mode, where you just set the duty cycle of the fan, for example, 50%, and around 50% of the voltage is supplied to the fan so that it doesn't run as fast. Another option is thermal cruise, and in thermal cruise you can specify that you want the fan to run, you can specify the target temperature of the system, so you can specify that you want the temperature to be around 60 degrees centigrade. And you can specify the tolerance of that temperature. And the tolerance could be, for example, 2 degrees. And then it means that if the system goes above 62 degrees, then the fan's engaged at higher speed. And if it goes below 58 degrees, then the fan's engaged at lower speed. It also has an option of fan speed cruise. And in fan speed cruise, instead of specifying the target temperature that you want the fans to try to maintain, you specify the target fan speed for each fan, and then it maintains the voltage so that the fan speed is maintained. And they also have the option called Smart Fan, and there's several different options, Smart Fan 1, 2, and 3. And it's kind of complicated. It has several levels for engagement of the fan. And I haven't added support for Smart Fan 3 to my patch because it seemed just like to be too complicated for the average user. So I'm not going to go into that too much. I think if you want to look at that, you should refer to Winbone data sheets. So how do they actually work? So generally, fans are rated for 12 volts. And 12 volts, it represents a 100% duty cycle. And most fans, they will still run reliably at 7 volts. And 7 volts, it's around 58% duty cycle. So if you're using this software and if you want to ensure that the fan gets around 7 volts so that it runs reliably, you will have to set the duty cycle to 58%. And 58% is obviously 7 divided by 12. That's how we get 58%. And most fans, few fans run at lower than 5 volts. So if you supply less than 5 volts to the fan, then it's not likely to start at all, and they're not likely to run at all also. So you have to ensure that you supply 5 volts, at least 5 volts to the fan if you want it to run reliably. So what is PWM, pulse width modulation? Pulse width modulation controls the amount of power that is sent to the load, and its voltage goes from high to low, to high very rapidly with a certain duty cycle. And pulse width modulation is more efficient when compared to rheostats, according to Wikipedia. So pulse width modulation is one of the settings that the fan speed control could be done with. So in the manual mode of the chips, you can control the duty cycle directly through software. So you specify that you want the fans to run at 100% duty cycle, or at 40% duty cycle, or at 50% duty cycle. And software-based monitoring loop would be required to accommodate reduced noise and excessive heat during high workload. So if you use in the manual mode, then it means that if you're doing some compute-intensive task, then you will have to increase the duty cycle of the fan so that the system doesn't overheat. And then if you aren't doing anything, if the system idles, then you will have to manually reduce the duty cycle of the fan. So you will have to run some kind of monitoring loop in the software. So that's what speed fan on Windows does. It can only do that kind of thing. It cannot do non-manual mode for these chips. And settings for each fan output, it includes in the manual mode, it includes the duty cycle itself. And then some chips, they have a selection of pulse width modulation or DC mode. And if you have a selected pulse width modulation mode, then you can additionally select the frequency of the pulse width modulation. So in another mode that is available, other than the manual mode, is the thermal cruise mode. And in the thermal cruise mode, you configure the chip to do the monitoring loop instead of doing the monitoring loop yourself in the software. Settings that are available in the thermal cruise mode is the target temperature and tolerance. So for example, you can say that the target temperature you want to be 55 degrees centigrade, and the tolerance would be plus or minus 2 degrees centigrade. And it would mean that if the temperature goes above 57 degrees centigrade, then the fans will engage at a higher speed than otherwise. And if it goes below 53 degrees centigrade, then it will engage at a lower speed, or it will stop at all. And then there's also settings for fan startup speed, startup duty cycle. And generally, in order to have the fan started, you need to have more voltage supplied to it than to maintain the speed of the fan. So for example, in one of the previous slides, I mentioned that most fans they still run at 5 volts, but some fans they will not be able to start at 5 volts. So if you supply the fan with 12 volts, or if you supply the fan with 7 volts, it will start. And then if you lower the voltage to 5 volts, then it will continue to run. But if you started at 5 volts, then it might not be able to start because 5 volts may be too low for the fan to start. And other settings include stop values. So for example, 40% is the lowest value. So when the temperature reaches, in this example, for example, 53 degrees centigrade, then if the fan stop value is 40%, then it means that the fan will be, after the temperature goes below 53, then the fan will be maintained at, running at 40% duty cycle. And if you set the fan stop value to 0%, then it will turn off completely after the temperature goes below 53 degrees centigrade. And there is also setting of whether the fan should be turned off completely. There is also setting for stop time, step down time, and step up time. And that is the time that is used to increase and decrease the voltage of the fan. So the third option, the first option was manual control. The second option was thermal cruise. And the third option is fan speed cruise, as I mentioned previously. So in the fan speed cruise, you can have a setting for target speed and tolerance. And you can also have a setting for step down time and step up time. But frankly, I've thought about the fan speed cruise mode, and it doesn't make much sense. I don't see the benefits regarding the fan speed cruise mode, versus a manual mode. Because in the manual mode, in the fan speed cruise, fan state generally they would not change much in the speed if you supply the same voltage to the fan. So once you determine that the fan runs reliably at 7 volts, and that it runs at a certain speed at 7 volts, then I think it would be just easier to use a manual mode instead of using the fan speed cruise mode. So in my patch, I haven't added support for fan speed cruise. I have only added support for manual mode and for the thermal cruise mode. So the fourth option is the SmartFan 3 in some of the chips that I added support for. And SmartFan 3 is an advanced self-adjusting algorithm with variable target temperature and tolerance levels. And since I haven't added support for SmartFan 3, you can look for details. You have to look for details at Winbot data sheets for additional details regarding this feature. So OpenBSD SysTL, AsiaBSD sensor fan control. So the fan controlling patch was released on in May 2009 on tech@openbsd.org mailing list. And you can see an address where you can download that message from with the patch, and you can just find that address by typing sensors.cnst.su/fanctl, and you can find the link to that patch. And in the patch, the following families of chips were supported: the W83 627HF. And this chip, it only allows you to have the manual mode, so you can only have the full suite modulation mode. And then another family of the chips is W83 627THF and W83 637HF, and it has I've added support for manual and thermal cruise mode in that chip, in those family of chips. And the third family of chips is W83 627EHF. And W83 627DHD, and I've added support for manual and thermal cruise mode in that chip, in those similar chips. So Dragonfly BSD, the fan controlling patch was ported from OpenBSD to Dragonfly BSD yesterday, and it's available in the FanCTL branch on my Leaf repository, Git repository, so you can get it from there, and you can apply it to your branch. And functionality that is currently supported is the same as with OpenBSD. So I'm going to proceed with the example using OpenBSD, but it should be basically identical to how you would use this patch with Dragonfly BSD. And the patch will likely be integrated into the master branch of Dragonfly BSD after some more testing. The patch is kind of a hack because it supports some functionality like, I'm going to go further into that something later. So integer values, the way it works, the way the patch works is that integer values pass back to individual sensors for sysctl. So when you want to change the one of the modes of the sensor, when you want to change the manual mode of the sensor to go from 100% duty cycle to 50% duty cycle, then what you would do is you would write sysctl space hw.sensors.lm0.%0 equals 50, and then sysctl 8 it will do a call. It will do a sysctl3 system call, and it will pass the integer value that you supply to sysctl, which in this example would be 50, and this value would go into the kernel, and it will go just as an integer value. It's not gonna. We're not going to be passing the struct sensor itself. So you would only be passing a single integer value back into the kernel. And then the driver, based on the type of a sensor that it is, the driver will automatically see what kind of value it is, and it will check for bounds and stuff like that. And then if everything is all right, it's going to apply this new value, and it is going to write this new value into the chip. So in the regular refresh procedure, sensors drivers check if a value has been placed and update the chip if it has been placed. And chip readings are always taken from the hardware. So in this patch, you will never see from sysctl output, you will not actually see the values that you pass to sysctl. So if you change the duty cycle to 58%, and if it doesn't actually change on the chip, then you're never going to see the duty cycle at 50% again. So if you, for example, set the duty cycle to 50%, but it changes to 50.1% because 50% is not the valid duty cycle in the specific chip, then you will only see the value that you read back as 50.1%. You will never see it as 50% because we always read the values back from the chip. So chip behavior, if you apply this patch and you reboot the system, chip behavior will not be modified by this patch unless the user specifically requests so via sysctl. So if you want to try this patch, but if you're afraid that it might do something bad to your system, then you can try to apply this patch and you can reboot the system and see what your settings are for the chip without actually damaging anything, without actually having any ability to damage anything. Generally, if you change the temperature, even if you turn the fans off, it's very unlikely that your system is going to be damaged. But it may happen, So next I'm going to provide some details about regarding the new sensors that have been introduced for the family of chips, which is W83-627HF and W83-627DHD. And this family appears to be the latest and most popular superior chips. And they provide the most settings for fan control, so I'm going to describe this family. And it's going to apply equally to the previous families, to one of the previous family. But the first family that I added support for, it only has a manual mode, so it's not going to apply to the first family that I added support for. So you can see that there's been several types of sensors that have been introduced. So the first type is the %0, 1, 2, and 3 sensors. These sensors, they provide the summary and the duty cycle of the chips. So for example, if you change the fan, if you're using the manual mode, then this on one of the sensors, on the system sensor, then you will see that the %1 sensor it is going to show you that the manual mode is currently engaged, and it will also show you the duty cycle of that sensor. Then another sensor that were introduced were the temp 3, 4, 5, and 6 sensors. And it allows you to specify the target temperature sensors, target temperature of the specific sensors. Then temp 7, 8, 9, and 10 it allows you to specify the temperature tolerance for each temperature sensor. And then the %4, 5, 6, 7, and 8, 9, 10, and 11 it allows you to specify start and stop values. And there's also the indicator 0, 1, 2, and 3 sensors that allow you to have a switch between pulse-width modulation mode and DC mode. And in one of the systems that I've tested, I noted that for some reason if you change it to DC mode, then the fans you cannot control the fans. But if you change it to pulse-width modulation mode, that you can control the fans. So sometimes you have to play around, and sometimes you have to toggle the switches to stop the fans to make sure that your settings they actually work. So here's an example of what output you get from the new sensors. So it's very small, so you cannot see it here, but we're going to zoom into it later. So controlling problems. Generally, a lot of chips, they are miswired. They're terribly miswired by motherboard manufacturers. So very often, all fans are controlled by a single source. So as you recall from the previous slides, there is several, most chips they provide several fan controls for several sensors. So you can have a separate fan control for system temperature, for system fan, and for CPU fan. And you can have a separate fan control for auxiliary fan and for a different fan, for a different CPU fan. But in a lot of motherboards, all of those fans, they are wired to the same, they're physically wired to the same source, to the same fan controlling source. So if you try to change the percent sensors other than one of those percent sensors, then it's not going to have any effect on the system. So all of the fans may be controlled by a single percent sensor. And sometimes fans cannot be controlled at all. So sometimes the chip supports fan control, and you can change these registers on the chip. But it's not actually going to stop the fan ever, or it's not actually going to affect the speed of the fan, because the motherboard manufacturer, they haven't wired the fans to the to the fan connectors. They haven't wired the fan controlling pins of the chip, of the hardware monitoring chip, to the actual fan controlling headers of the board. And theoretically, this stuff can cause bad interactions with BIOS, CPI, and some other utilities. But in practice, it tends to work on desktop hardware without any noticeable issues. And some BIOSes have an annoying fan error. So sometimes if you make the fan run at lower speed than it usually runs, when you reboot the system, the setting still stays in the hardware monitoring chip. So when you reboot the system, the fan is still running at lower speed. And some BIOSes, they check the speed of the fan when it reboots. It checks the speed of the fan. So if the fan is running at very low speed, then it may give you an error that there is a fan error. Instead of continuing with the boot process, it may give you this error and it may stop rebooting. And I'm going to have a live demonstration. Unfortunately, I wasn't able to get a box here to have a live demonstration here so that you can see how the fans are stopped. But I have this patch installed on my production box in Waterloo, Ontario, in my office, and I'm gonna show interaction with the fan controlling patch on the box, and we will monitor the speed of the fan with the other sensors, so that we can see if the fans stop, and if it doesn't stop, it's like that. So let's try it. here you can see the sensors. So you can see that there is a lot of sensors on this box because of this new patch. So you can see that the new sensors that I was talking about, this %0 sensor, %0 to %3 sensor, it represents the individual fan controlling pins on the hardware monitoring chip. So this specific chip that I have on the system has 4 distinct fan controlling pins on the chip. And you can see that there is one pin that's labeled as a system fan, another one is labeled as CPU fan, the third is labeled auxiliary fan, and the fourth is labeled as another CPU fan. So you can see in the description of the sensor, if you're not very familiar with OpenBSD hardware sensors framework, then this stuff that I've outlined, it's the description of each sensor. So in the description of this percent sensors, the first part of the description is the actual name of the fan, what kind of fan it is. Then this part, it shows you what setting currently this fan controlling pin is running at. So you can see that the first three fan controlling pins are currently running in the pulse width modulation mode. But the last fan controlling pin, it runs in the DC mode. And this item here, you can see that it's the current setting of this fan controlling pin. So the first pin is set for the thermal mode, cruise mode. The second fan is set into the manual mode, and the third fan is set into the manual mode, and the last fan is set into the smart mode. So the system itself, it only has one fan, or maybe it has 2 fans. It only has one fan. So we can only control one of the fans. So the system fan target is currently set into 38 degrees centigrade. And you can see that the system temperature, that is the system target sensor. So it is a sensor which you can modify. You can set it from 38. You can set it to, say, 48 or 60 or whatever. And then if you set it to 48 or 60, then because the system temperature sensor, this is a reading sensor, the system temperature sensor is below, if it would be below 60, then the fan will reach lower speed, and if it will be above 60, then it's going to be higher speed. So currently you can see that the fan runs at 1500 RPM per rotations per minute. So let's try to change some settings so that it will run at lower speed. So you can see here in the active refresh, you can see the current speed of the fan. So in this example, I can set the thermal cruise mode of that sensor, of that system target temperature from 38 to 46 degrees. And I can set the %4 sensor to 16 and %8 sensor to 12. So let's see what's going to happen. So you can see after I issue this comment, I get the result of the current readings. And you should also notice here that it's going to be soon, it's going to be changing, the speed is going to be changing. So the %0 sensor, it indicates the current value that is being supplied to the fan. And you can see that it goes down. And soon it will reach low enough that the speed is going to be reduced. It reaches 11%. And then the speed of the fan reduced from 1500 RPM to 1100 RPM. And it may not sound like a big change in RPM, but actually, when I tested this back at home, it results in a very noticeable noise. When the fan runs at 1500 RPM, then it's quite noisy. But when you change it to the setting that I've changed it to, then when it runs at 1100 RPM, it's much quieter than it runs at the previous speed. The internet is quite slow across the subject.
I'm interested in what kind of tool. Is that top-like monitoring tool?
Oh, this stuff?
Yes.
It's SciStat.
SciStat?
Yeah.
I don't know well the common application.
It's available in all BSDs. It's available in FreeBSD also.
Yeah.
So it's in OpenBSD. You can the sensors framework is integrated into several tools, and SciStat is one of them. So you can monitor everything with SciStat. Like with SciStat, the mstat is like a popular command, popular display. So have you seen this screen?
SciStat.
Yeah.
SciStat. Yeah,
Yeah.
I know.
So yeah.
Sensors. It depend on OpenBSD.
Well, the sensors framework, it was ported as a Google Summer of Code project to FreeBSD. So as a part of the project, I also ported the sensors view to FreeBSD. So it can be worked out in FreeBSD also, but obviously it's not integrated into FreeBSD because the patch was backed out. So yeah. But you can still, I heard from a number of people that they still, they applied that patch and it worked for them, so they may be still using it. So if you're interested in that display, SciStat display with sensor, then you can certainly apply that patch to FreeBSD and you can use it. So, yeah. And generally, I ported, as I noticed in my slides, I ported the fan controlling interface to Dragonfly BSD yesterday, and it's really pretty straightforward. And by seeing the Dragonfly, there is not much difference between FreeBSD and Dragonfly BSD. So if you see the Dragonfly BSD patch for the fan control, you can very easily integrate it into FreeBSD almost without any time. So if you find out that patch that I ported the sensors framework to FreeBSD from OpenBSD originally, and you get this CTL patch for Dragonfly BSD, then you can easily integrate the two into FreeBSD, and you can easily use it on FreeBSD too. So, yeah. Do you have any other questions, or do you want to see anything else for the fan control here?
How about to implement the daemon for monitoring the fan contour temperatures and like powered do you power D and fan something like the fan D?
Okay. No, I didn't work for any towards any daemon for fan control yet. And one of my reasons for that is that I wanted those chips, they can already automatically monitor the speed of the fan, and they can already automatically monitor the temperature of the system, and they can modify the fan speed as a result of differences in the temperature of the system. So I just wanted to use the in-chip fan control. So that's the reason why I haven't worked on the specific daemon for fan control. But obviously some chips, they don't allow you to have in-chip monitoring of the temperature. So for those chips, indeed it will be of value to have the daemon that will allow you to monitor the system temperature and will modify the duty cycle of the fan. And also one other consideration is that if you write a daemon, you will have access to more sensors than the chip has. So for example, you may have several hardware monitoring chips, or you may also have several CPU sensors, or some other additional sensors. And if you have a daemon, then you can also monitor system load, and you can modify the fans according to system load. So you obviously have more flexibility. You would have more flexibility if you write a daemon. And you can easily write a daemon, and you can use this framework to modify the speed of a fan. So the interface is really pretty simple. So the way it works is, I've mentioned in one of my previous slides, is that you simply pass an integer value for the sensor. So if you want to change the sensor, the percent sensor from 100% to 50%, then all you do is you make a sysctl call, and you supply the new value for the sensor. And it's just an integer. You just supply an integer, and you set it to size 4. And this integer is going to say 50, and the size is going to say 4 for sysctl3 call. And it's going to go into the system, and the driver will pick it up in the next refresh procedure. So it's going to set things up and work with that. So one of the nice features about this interface is that you don't have to actually change yourself. You don't actually have to specify whether you want to have a manual mode or a thermal cruise mode explicitly. So if you modify the percent sensor, if you manually modify the percent sensor, so as you recall when we started this demonstration, the percent zero sensor was set at 100%. And it was set at 100% because this sensor, this thumb header, it was set to the system target temperature was set to 36 degrees, and the system temperature at that time it was around 35 maybe, or how much was it? Around 40 maybe. So the system target temperature was much below the actual temperature. So that's why the fan was running at 100%. But right now, because we increased the system target temperature, and the system temperature still stays at around system target temperature, and it doesn't go above the tolerance. So if the system temperature, if we do some compute-intensive task, and the system temperature will raise to 48 or more than 48, then because we have the system target temperature set as 46 and the tolerance set at 2 degrees, then this value will go up. So for example, let's try to do some SSL kind of thing, OpenSSL. So OpenSSL speed is going to do some compute-intensive task, and it's going to use a lot of CPU resources. And we will try to run CPU OpenSSL speed to take a look how the temperature is going to increase and how the speed of the fan is going to increase. So I'm starting to run it now. So you can see that the system temperature is going to, the CPU temperature is already increasing to 61. 61.5. 62.5. The system, 63. The system temperature is still just 46. So this value is not going to go up until this value reaches above 48. So it goes 63, it's going high. 64. So one of the other advantages of having a daemon that will monitor these things for you is that the daemon will be able to actually take a look at all of the temperature. So you see it now 47, so it might go, the fan might run up soon. I think I will probably have to stop it when it reaches around 70, because after it reaches 70 it might just burn or something. So one of the advantages of having a daemon, as someone mentioned, is that you will be able to take a view at all of the sensors, and you will be able to modify the speed of the fan based on all of the sensors. 48. So I think it's going to go up soon, so I think we'll try it. 72 is when I'm going to stop it. 70. I think maybe it went down because some of the thermal protection on the processor got engaged. I think that's the reason. So generally, the hardware itself, it has a lot of fail-safe conditions. So it's not very likely that you will be able to actually burn your processor with this experiment. This box is currently located in my office, and we have air conditioning set up there. So maybe the air conditioning prevents it from going too high, from the system temperature going too high. Okay. So let's try to modify the target to have a somewhat lower value. We can set it to 40 degrees. So you see it changed to 40 now. And now this value goes up. And it goes up slowly. And you can see that the fan went up. So it's 47 now. And this value goes up slowly automatically by the chip itself. So I'm not changing anything. Like when I write this comment, what happens is this value set, they get passed to the data structures that the driver is going to look at. And then the driver, in a single refresh procedure, the driver writes these values, these new values that they supply on the command line, to the chip. And after that, the driver simply reads the values back from the chip. So it means that because the value was changing slow over time, it means that the chip itself, it automatically changes its value slow over time. So let's try to do the manual fan control. Let's try to just stop the fan and see what happens if we just stop the fan. So I'm writing sudo systctl hw.lm1.%0 equals 0. And after I have this command executed, you should take a look at the sensor. It's going to go, the value of the sensor is going to go to 0. And the sensor description, which is this part, it's going to change from thermal to manual. So you see it changed to manual. But it changed to manual, but it still says that it's... So you can see that the fan sensor disappeared because it went to 0. So the fan is currently off. But the system is still idling, so it doesn't, the temperature doesn't really raise all that fast. We can try to set it to 5%. At 5% it's not going to start. But you can see that it changed here. And it changed, instead of changing to 5%, it changed to 4.71%. Because 5% is not a valid value from 0 to 255. So this manual mode, the way it works is that you write to the register a value from 0 to 255. And 5 is not a valid value there, so the value that is closest is 4.71. So that's a value that the chip, that was written to the chip. So you can see that it's, this value is too low for this fan to start, so it didn't start. Let's try to set it to 7. It's still not going to start it at 7. It doesn't work at 8. 9. Doesn't start at 9. 10. So we set it to 100 and you're back. But then if we set it to 10 after that, then it is going to work. And the reason is that for the 10 to start, we need to supply higher voltage and for the 10 to continue running. So you can see that the system temperature is now at 50 degrees. So we can do now the thermal cruise mode again. So this value is going to go from manual to thermal, and the value is going to increase slowly to indicate that it's going into. So right now in the thermal cruise mode, you can see that the value that the system decides to run at, that the fan thinks that it should run the fan on, is 100% due to cycle, because the system target temperature is 46, and the sensor reading is 49, and the tolerance is 2. So when this value, when it's going to go below 44, then it may turn to lower level. So do you have any questions?
It looks like very useful for server system management. And how about to implement your sensor framework and this WinChip? WinBond modules as previously kernel modules.
Okay.
It can be imported to post-correction and the benefit for all people all over the world.
To what? What again?
If you could implement this feature as previously kernel module,
Okay.
we can add it to the post-correction.
Oh, post-correction, okay.
Yeah, and the user all over the world can use it.
Okay. Well, the complicated thing is that it's tied to the sensors framework. And the sensors framework, I'm not sure, I think I'll have to work on it, like to make it workable as a module. Generally, sensors framework, it's intended to be used as a part of the kernel, as a non-optional part of the kernel. So I'm not sure how much work it will be required to have it be optional. But possibly you and someone else can take a look at that, so yeah. But as a general patch, you can just download the patch and you can apply it to your system, and it's going to work. And I think it still should apply to FreeBSD 8. When I wrote the patch, when I finished writing that patch, it was the time when FreeBSD was branching for Erlang 7. So right now we have Erlang 8. But I think it should still apply pretty much good for Erlang 8. I don't think there has been much changes. Most of the stuff that you're going to find the conflicts when you try to apply the patch are going to be in the make files. So the patch itself, it introduces several new files. And obviously you will not have any conflicts with the several new files. And the API that I was using from FreeBSD, it wasn't that much different. It's not that much, it shouldn't be different between 8 and 7. So you shouldn't have much problem with applying the patch other than the make files. Any more questions? Yeah?
These sensors are accessible via SMBus, as I understand.
It's accessible via SMBus and ISA ports.
So maybe it could be easier.
Well, on OpenBSD it's accessible via both SMBus and ISA, and on Dragonfly it's only accessible via ISA.
So maybe it could be easier to implement a library doing the same and provide some interface for tools but not moving it to kernels. I understand it was one of the reasons why it was backed out from FreeBSD.
Right. Well, that's a whole another question that's not related to the time control. So well, there's obviously benefits and contradictions about those kind of things. So the reason is on OpenBSD, when you install OpenBSD, all of the sensor pages work. But if you have it as a library, as an optional library, then someone has to write it first. And then it's also questionable how much access you want to have to give to libraries into the kernel. So for example, all of the sensors that I gave in the demonstration that I tried, they are all connected by ISA ports. So they aren't actually available in SM bus. Some sensors, they are available in SM bus, but in reality, it's much more common to have the sensors available on ISA ports and SM bus. So, yeah.
And what other sensors available on that infrastructure in OpenBSD?
Well, in OpenBSD we have around 75 drivers that they use in the sensors framework as of 4.6, and it's going to be probably more than 80 drivers using the sensors framework as of the upcoming 4.7. So there's a lot of drivers. There's a lot of different drivers. Some of them are SM bus related. Some of them are ISA superior hardware monitors, and some of them are different kinds of sensors. So yeah. Do you have any specific questions?
No, I'm just surprised with number of 70. It's like everything. So you're monitoring just whatever, not especially temperatures, but every kind of monitoring, every event.
No, not every event. Most of the temperature sensors, they're by far the most popular sensors. So I think I have a graph somewhere. I can show the graph of the sensors, of the types of sensors. So 50% of the, OpenBSD 4.6, it has 75 drivers using the sensors framework. And this chart, you can see that it has a sensor type popularity in OpenBSD 4.6 based on the number of drivers used in each type. So temperature sensors, they used in 50 of those 75 drivers. And then 10 and voltage sensors are used in 26 and 25.
With name driver, you mean something like a Winbond chip. Yeah.
Driver, it means a driver with a different name and with a different source code file in the tree. So some drivers, they support several chips, whereas others, they support just one chip.
Just quite large amount, I would say.
Yeah, basically, like if you boot OpenBSD on any computer, and it will be more unlikely for you not to have sensors than to have several sensors. So a lot of the computers, they would have, right now, they would have at least 2 sensors. So if you, for example, have an Intel Core system, then you would have one sensor, when you're most likely to have one sensor, which is going to be the Super I/O sensor, and a chip, and then another sensor would be the CPU sensor. And then some notebooks, they may have also sensors in the wireless cards. Some other sensors, you can have USB sensors, you can have USB temperature sensors, and USB hydrometers. You can have USB humidity sensors. So yeah, just anything. In 4.7, there's going to be a USB. There's going to be a new driver introduced that has supports for USB temperature and humidity sensors. So you have any kind of sensor.
And this framework is just interface to user level, providing set of CCTLs to access this information. It's not doing some other stuff.
This framework, it basically provides you kernel interface, and it provides you provides you. It has the CCTL as a transport layer for the stuff. Yeah. But that's not related to the talk. The talk is about the sound control. So, any more questions about sound control? Yeah.
Did you measure how much power consumption actually goes down?
Power consumption going down. That's a very good question. I think many fans, they usually would run from, say, 2 to 5 watts. So if it runs at 4 watts at 100% mode, then it may run at, say, 2 watts if you're used to speed. So you may kind of save a few watts if you turn the fans down. But the other thing is that when the CPU itself, I think when the CPUs itself or different components, when their temperature increases, so if the CPU is running at 30 degrees, then it may consume less power than if it runs at 65 degrees. So I've noticed that I have a thing that measures the power consumption of the box, and I've noticed that on my AMD Phenom box, when I just start the system, after it boots, it consumes about 139 watts. But after it runs for a few minutes, then as the system gets hotter, it starts consuming 142 watts. So it seems that when the components get hotter, they may consume more power. So it's not really clear how much voltage, if you're actually going to be saving any power with using this approach. Because you may be saving power on the fans, but then the components may consume more power as a result. So more research is needed into that area. So, but that's a very good question. Thank you. Any more questions? Yeah?
I have a question. I have a suggestion. I wonder if implement temperature monitoring system to top command. I have improved top command, but simply only CPU temperature and frequency. Please see also. See.
Oh, is it on BSD?
Yes.
Oh, okay, that's pretty nice. Yeah, that's a good idea. Yeah, that's interesting. Well, on OpenBSD, because we have so many sensors, it would be unreasonable to have them in the top. So, but that's a very good idea.
Thank you.
You're welcome. So, any more questions or comments?
Haven't any like invented some power monitoring, so current monitoring or only voltage. So is it possible to monitor system power consumption?
Oh, system power consumption. No, I don't think so. Not in the hardware monitoring chip. I think you could do that via ACPI somehow, but I'm not exactly sure.
On laptops, it's possible we are better monitoring, but on desktop, there are no
yeah. Sure. Yeah, absolutely. Any more questions? I think you should publish a patch somewhere. Did you publish it on the mailing list?
Oh, okay.
Okay. Yeah, sure. Well, any more questions? Well, I guess this concludes the presentation. Thank you.